right, solids lab. Today is the thin walled pressure vessel lab. Okay, the objective of today's lab is to calculate the internal pressure of a Coke can, and that is capital Coke. All right, so our theory. All right, doing a little online checking, it looks like we should be measuring somewhere between 25 to 60 psi. Now it's the high side if it's room temperature. This Coke can has been room temperature, so I'm going to say 50 psi approximately for room temperature. And I want you to do your own search to find your theoretical calculation, internal pressure value. Okay, I'm going to say 50 psi. All right, now remember, for thin wall pressure vessels, we first have to check R over T greater than or equal to 10. Okay, because if it's not, that changes all of our calculations. So I measured the Coke can, and I get a diameter of 2.602 inches. I actually measured it at 66 millimeters, so there's the conversion. Okay, the wall thickness, we're going to have to measure again after it's opened, but it should be about 0.00787 inches. That's about 0.2 millimeters. Okay, so that means our R over T value is going to be 2.602 inches divided by 2 divided by 0.00787 inches, and that is equal to, heck if I know, because I don't have the calculation written out here. Oh, there we go. 2.602 divided by 2 divided by 0.00787. 165. I would have to say that is greater than 10. So this is a thin wall pressure vessel. So that means we can use sigma hoop is equal to PR over T, and sigma long is equal to PR over 2T. Okay, now we've already done the R over T calculation. That's 165.311. So we're just going to throw in our pressure here. So sigma hoop is equal to pressure, that's 50 psi, times 165.311, that's our R over T, and it's unitless because they were both inches, and that is equal to times 50, 8,265.6 psi, which means our sigma long, which is 1/2 of sigma hoop, 4,132.8. All right, now we cannot measure stress, we can only measure strain, and we have strain gauges. So how do we go from stress to strain when we're in the elastic region? And we are in the elastic region because our cans are not bulging and deforming. It's Hooke's law. Stress is equal to the modulus of elasticity times strain. So my strain hoop is going to equal to, okay, according to our textbook for aluminum, we should have a modulus of elasticity of 10.6. Bet you it's the weaker one, so I'm going to say 10,000 KSI. So that means our hoop is going to be 8,265.6 PSI all over 10,000 KSI. Remember, a K is 1,000 Ps. 8.2. Okay, so that's going to be 10 to the third PSI per KSI, which is equal to 826. Hold on. Yeah. Times 10 to the negative 12. Inches per inch, right? Sorry, I'm checking my math. So I'm going a little slower than it's probably preferred. And E long would just be half of that. or 413 times 10 to the negative 12. Oh, I see what I did. Fantastic. Okay. 8265 divided by 10e6. There it is. All right. Woo. I was wondering why my numbers were so off. All right. So that's to the negative 6 as well. Inches per inch. Okay, those numbers are much more reasonable. Sorry for my poor math skills. Okay, now here's the thing, ladies and gentlemen. Do you remember that when we have a stress element and we put it in tension, what's going to happen? It is going to get skinnier and longer. And this is Poisson's ratio. Well, the phenomenon's not Poisson's ratio. The calculation is Poisson's ratio, which is going to be nu negative E lat over E long. Okay, now this is longitudinal, not, it's different long than the long on your soda can. So if I come up here and let's use red for my soda can. All right, here's my soda can. All right. This is our element, which means this direction is the long and this direction is the hoop. Okay. And let's label axes here, X and Y. So strain in the X direction is going to equal to E hoop minus Poisson's ratio E long, right? Because this wants to stretch out in every direction, which means in the hoop direction it's trying to stretch out, but it's being pulled back by the longitudinal direction. Similarly, EY is going to equal to E long minus nu E hoop. Okay, is that making sense? Psh, sticks a little Coke can. That's a terrible tab. Anyway, there we go. So my EX calculation, how about we have our theoretical strains? EX is equal to E hoop. Which one was E hoop? The 826. 826 times 10 to the negative 6 minus Poisson's ratio for aluminum, using the same one that we used for the modulus elasticity, is 0.35, 0.35 from your textbook, times E long, which is the 413. And that's equal to, so we have 826 minus 0.35 times 413, and that is 681 times 10 to the negative 6 inches per inch, or 681 microns, and EY will be 413 times 10 to the negative 6 minus 0.35 times 826 times 10 to the negative 6, which is equal to 413 minus 0.35 times 826, 124 times 10 to the negative 6 inches per inch. All right. So these are the values that we're hoping to measure when we open up our soda can in lab. All right. So we need to make sure that we note our Poisson's ratio from the book, our modulus of elasticity from the book, and our three equations, thin wall pressure vessel, hoop, thin wall pressure vessel, long, and Hooke's law. Conversions are not an equation that need to be listed in your report. This